We have Darren Yeardsley from Waterware. Darren is the technical genius behind many of Waterware's specialist products. His analytical brain and practical ability has been instrumental in the development of innovative and sustainable system solutions and designs by Waterware. Darren is motivated by educating and supporting the market with technical and design knowledge, whilst still delivering solutions that are functional, ingenious, and beautiful. Darren, good afternoon. Are you there?
Good afternoon. I really want to meet
Hello.
that guy. That sounds impressive.
Yeah, sounds like a cool guy, I guess, eh? I'm gonna.
I don't know who wrote that.
Yeah, I'm gonna let you know. Sorry, I'm gonna let you go ahead with your presentation, then we'll chit chat a little bit more at the end.
Okay.
Thanks.
All right, I'm Darren from Waterware. We specialise in high-capacity hot water systems, amongst other things. In the past, we've done a lot of systems which were all based around gas technologies, sometimes diesel as well, in the long days past. But as new technologies enter the market and as the market starts demanding renewable solutions, then we've started to develop new things to meet the needs of the market. And so today I'll present a renewable hot water system, which is a combination of technologies based around an engineering tool, which we can model the performance, and then we can use the output from that tool to then quantify what the capital cost is, what the running costs are, what the carbon footprint is, all sorts of interesting metrics which you can then use with the client to put a value proposition around different ways of producing hot water. So just as I get started, one thing I just want to cover off is the difference between centralised and decentralised hot water production. So there's a number of sort of technical aspects which I'll just talk about, and I just want to just cover them off, so when I'm talking about these things, you've got some sort of idea about some sort of framework to hang the knowledge on. So the system which we're promoting is used in multi-unit residential application. So typically apartment building or rest home or wherever you've got a large number of people who you're trying to shower. And when we have a strategy around how we're going to produce that hot water, there's two main types of system which get used: centralized or decentralized. And so I'll quickly cover off what the difference is and what the strengths and weaknesses of each type of solution is. So the easiest to understand and the most common, the most similar to what you get in a house is decentralized hot water production. So that's basically a hot water cylinder which is allocated per unit. So if you've got a 50-unit apartment building, you'll have 50 electric hot water cylinders. Through the building, you have a network of cold pipes which supply cold water into the apartment, and then you feed the hot water cylinder, which typically is driven with an electric element. And then that it heats the water basically at point of use. So each apartment is standalone with its individual hot water production systems. Contrast to that, we have a centralized the user opens the tap, the hot water comes out without any sort of delay. So the key differences between these types of systems, well, when we're thinking, one of the key drivers for going centralized rather than decentralized is capital efficiency. Once you tip over about, if you're going to do a gas solution, for instance, once you tip over about 20 apartments, then the cost of doing a centralized system is cheaper than doing a decentralized system. So that's one of the key drivers of why historically, when you look at apartment buildings and hotels, hospitals, rest homes, all these sorts of places, typically once they get above a certain size, they'll have a centralized hot water system. So one of the advantages, another advantage of having a centralized system, especially when you're looking into the apartment market, is you get a lot of space efficiency. So with a decentralized hot water system, and you've got an electric hot water cylinder, one per apartment, you have to provide space within the apartment to house that hot water cylinder. So every apartment has a hot water cylinder covered. as the cost per square metre of apartments go up and up, that becomes more and more valuable real estate. And if you move to a decentralised hot water production, then you liberate the space inside the apartment for use for something else. So it means you can make either your apartment smaller or more roomy or whatever. That space is now no longer required to house a hot water cylinder. And in terms of gross footprint, when we look at the size of what a plant room would be to supply that hot water, if you amortize it out on a per apartment basis, it's much more space efficient than doing individual hot water cylinders. So one of the drawbacks of having a centralized system rather than a decentralized system is if you have a problem with the centralized system in the plant room, you take out the hot water production for the whole building. Where if you've got decentralized and you've got 50 electric hot water cylinders, if you have a problem with one of the electric hot water cylinders, it just stops hot water production in that one unit. All the other 49 apartments run no problem. So there is some techniques which gets used to help reduce that risk. Typically what you find with centralized hot water production, there'll always be multiple appliances and multiple hot water cylinders which are installed in cascades. So if you have a problem with a particular appliance, it doesn't take out the whole production, it just reduces the total capacity of the system, but you can still limp along until the system gets restored. One of the other things to consider with a centralized system is you need to have a return pipe. So you're actually reticulating hot water through the building all of the time. And the reason for that is if the apartment you're feeding is a long way away from the plant room, you don't want to wait for the hot water to leave the plant room, travel all the way through the building and then finally arrive at the tap. So the way which that is overcome is you circulate water through the building all the time. So there's a main pipe normally that goes through a riser, and then there'll be a return pipe which comes back down through that riser. And as the water circulates around, it means that now when you open a tap, it only has to move from the riser to the apartment, not from the plant room to the apartment. And so that radically reduces the amount of wait time. But there is a cost in that, and the cost is heat loss. You do get some heat loss out of the ring main pipes. But typically what we find once you go over a certain size, the heat loss out of your ring main and your plant relative to the heat loss out of multiple cylinders is pretty much a wash, or once you go above a certain size, it's actually more efficient in terms of heat loss to go centralized. So that's a little bit counterintuitive, but when you have, let's say again, 50 electric hot water cylinders, they all radiate heat at the rate of an individual cylinder. And so you'll find that when you have one larger hot water cylinder or two larger hot water cylinders, the rate at which they radiate heat on a per litre basis of storage is actually significantly lower of an individual hot water cylinder. So when you scale that out, what you tend to find is your ring main losses are more than offset than what multiple cylinder losses would be. So pretty much the heat loss question typically isn't a deal breaker in terms of a metric we pay attention to. Okay, so another technology which is central to our system is air-to-water heat pump. So almost everybody's familiar with heat pump technology in general. Most heat pumps which people have experience with are air-to-air heat pumps. So you have an outdoor unit and then you have an indoor unit with a fan inside, and that blows hot or cold air on you. So the sort of heat pump which we're talking about is air-to-water heat pump. So rather than producing hot or cold air, it produces hot or cold water. And in our application, we're producing hot water, which we then use to recover our hot water system. So one of the key points of air-to-water heat pumps, one of the key advantages of air-to-water heat pump is electricity utilization. So when you look at a heat pump technology, normally there is an efficiency rating with it, which is stated as COP, coefficient of performance, and it's normally stated as a ratio. So in the hot water application, the air-to-water heat pump which we use has a COP of 3:1. Now, what that 3:1 ratio means is 1 kilowatt worth of electricity given to the heat pump will yield you 3 kilowatts worth of hot water. So if you're going to state that as an efficiency, then it's 300% efficient, which obviously doesn't make sense. How can you get more energy out than what you're putting in? So when you look at electric element, which is inside a hot water cylinder, for instance, that will have a COP of close to 1 to 1. They're typically 100% or 99% efficient. So if you give it 1 kilowatt worth of electricity, it converts that directly into heat, and it does it in a super efficient way. So you might yield 995 watts, for instance. Okay. When you have an air to water heat pump, if you give it 1 kilowatt worth of electricity, it's not converting that directly to heat. What it's doing is it's running a process. And the process is it takes a large quantity of air and it scrubs the energy out of that air. So you might have, let's say, 10 cubic meters of air, which is entering the appliance at 7 degrees, and then it gets expelled from the appliance at 4 degrees. Now that difference in temperature from that large quantity of air has a certain amount of energy. And that energy now gets transferred into the water flow, which makes the water temperature go up. Now, the real magic of the system is it does it at a rate much higher than what you can do if you are converting it directly to energy. So the energy which an air to water heat pump harvests is actually from the air outside. So the process runs at this coefficient of performance, where if I provide the heat pump 1 kilowatt worth of electricity, it will return to me 3 kilowatts worth of hot water. So that is it's like magical technology, especially when we're looking at in the application which we're doing. So in terms of electrical utilization, if I've got 1 kilowatt worth of electricity and I had two choices, one, I can send it to an electrical element that will yield me 1 kilowatt worth of hot water, or I can send it to an air to water heat pump and that will yield me 3 kilowatts worth of hot water. Then it becomes pretty clear about the power of these appliances and why they're starting to get used more and more. So in terms of capital cost, these units are quite expensive compared to what an electric element would cost when you're comparing on a cost per kilowatt basis. But because of this yield function, they have much lower running costs, so 30% running cost of what standard electric element would have. And also it allows you to use it to capture more energy than what you could if you were using just straight electric. So one of the limitations with electricity is actually getting enough amps into the building to produce, to run all of the electrical appliances that we need. And one of the advantages, obviously, with an air to water heat pump is that we can supply it a third of the energy that we would if we were just going to use electric elements. So that gives us quite a bit of headroom when we're talking about combining with other technologies, which I'll get to later in the presentation. Okay, so the reason why air to water heat pumps haven't been used in this application so much in the past is the older refrigerants which were available, specifically R410A and a more recent refrigerant R32, they have limited temperature which they can produce. So both of those gases top out at about 60 degrees, slightly over, maybe 62 degrees. When we're producing hot water for potable applications, for taps and showers, there is a requirement to be able to heat the tank up hotter than 60 degrees. And this is for Legionnaires. So there's a bacteria which grows in the water, and we have to sterilize the tank to make sure that it's safe for use. So with these older technologies, these older gases, if you were going to use this type of appliance in this application, you had to back it up with an electric element. And because the electric element COP is only 1 to 1 and your heat pump is 3 to 1, the overall COP of the system when you're using this electric boost drops down quite a bit because you have to use the electric element to sterilize the tank. Okay, so relatively recently, there's been a change in the type of refrigerants which have used, and it's been driven mostly through climate change. So there's a score which is given to refrigerants called GWP, Global Warming Potential, and it's a continuum, and it's a measurement of the damage which the refrigerant does to the environment if it's let off. So the gold standard is CO2 that has a GWP of 1. And the older gases like the R410A, which I mentioned, is kind of a legacy gas that has a score of 2,500 units. In between, we have R32, which is kind of the most common gas available now, and that has a score of 650 units, I believe. In the Paris Climate Accord, there was a new standard brought in, which the goal is to comply with by, I believe it's 2028, and it's to be below 500 units for GWP. So there's been development of these new gases, and the new gas which we have in our appliance is called R290, which is propane, basically LPG. And the real reason, like one of the key drivers for using this gas is it has a very low GWP. So it has a GWP of 3. So it's basically inert. It's very close to CO2. But one of the other good properties of this gas is it produces hotter water than what the older appliances do. So the new air-to-water heat pumps will produce water up to 75 degrees. That now gives us enough headroom to be able to comfortably sterilize the tank, and it really opens up the market now for hot water production using these appliances. As the outdoor temperature goes down, the efficiency of the appliance goes down, but they still remain operational right down to -15 in hot water production duty. So they're a fairly robust appliance in terms of operating range, in terms of output temperatures, and in terms of the sort of environments which they'll work in. And it really forms a key part of the system which we put together for hot water production. So these two technologies together, centralizing hot water production and then using air-to-water heat pump as the main appliance, is basically the backbone of what the net zero concept is. Okay, so we have a combination of technologies which we're using. One of the things which Waterware has as an advantage in a supplier is we've got a very broad basket of products, and it's a bit of a double-edged sword because it's hard to be a specialist in everything, but what it does allow us to do is create systems using multiple components from multiple industries and then put together these innovative solutions. So this particular system is a combination of solar PV, which produces electricity, which we then run to the high temperature air-to-water heat pump, which we then store with large capacity hot water cylinders. We can then distribute that water through the building using this ring main centralized hot water concept. And then we can charge the users for the water using a wireless or wired water metering system. So that's the advantage we've got as a company, is we've got all of these products in our portfolio, apart from solar PV. But what we do is we drive the specification about the shape of the solar PV system. And we do that from specifying what size heat pump is required for the job. So that's basically the main components of the system, where we have solar PV as the creator of the energy. We have the high temperature air-to-water heat pump, which converts that energy into hot water. We store it in large storage cylinders. We then distribute it through the building at the right temperature for use, 55 degrees, and then we can water meter to charge back if required, depending on who the client is. Okay, so the engineering tool that we've developed, when you combine these technologies together, one of the key things is getting the right proportion of storage and recovery, and then that drives your solar PV system. So we have this engineering tool which allows us to create a model for the size of the system required to produce the hot water that the building uses. So we start with total occupancy, and then we allocate a total number of litres of water per person at 60 degrees. There's an industry standard sizing guide, and typically that runs from 25 litres per person at 60 degrees for entry-level backpacker sort of accommodation, up to 50 litres per person for more very high-end sort of residential applications. So depending on the quantity of people who we have in the building and what level of accommodation there is, that drives our requirement for hot water. And typically in multi-unit residential, the way which you serve that hot water is in 2 peak periods. So typically you'll have a peak period in the morning, which might run from 6 a.m. to 8 a.m., 2 hours long. Then you'll have a peak period in the evening, maybe 6 p.m. to 8 p.m. And typically that's half as many people as what you'd shower in the morning. So when we develop the model for the system, we size it so that we can shower the total occupancy of the building if every bedroom is full, and we can shower them, everybody in that first peak period. And once you've got that, that total capacity, you know how much water is required to deal with that peak period, then you can start designing the system to produce that hot water. And we can create a model which gives you the amount of energy required to produce that hot water. So into our model, we're NIWA very kindly publish all sorts of climate data. So they publish groundwater temperature, they publish air temperature, and solar hours per mean radiation values, all region by region. So we can specify how many people we have, what literage of hot water, and which region it's in. The tool then goes away, looks at the climate data, and it comes back and it creates this power requirement model. Now, the power requirement model will tell you how many kilowatts is required for my heat pump to produce the hot water to meet the peak period in the morning. So you can see that it's a curve, a bell-shaped curve pretty much, where the energy required in the summer months is less than the energy required in the winter months, which is intuitive. The key drivers for that is groundwater temperature is colder in winter than it is in summer, so we have to rise the temperature up higher to meet that 60 degrees. And the second factor is the air temperature is colder in the winter than it is in the summer, and that affects the COP of the appliance. So the overall efficiency of the heat pump. As you can imagine, if the air around the heat pump is very warm, it's very easy for it to convert that 1 kilowatt of electricity into 3.5 kilowatts of hot water. Where if that air is very cold, then it's harder and less efficient. And so that creates this bell-shaped curve where we get a model of exactly how many kilowatts per month is required to produce the hot water to shower everybody in the morning. Okay, so the second model which is created is a power production model. So once we know what the power requirement is, we can then use that information along with the mean daily global radiation figures to specify the size of the solar system required to produce the same amount of energy which our heat pump is consuming. So you can see this is an inverted curve where we have more production in the summer and less production in the winter. Again, that's quite intuitive. You have longer days in summer, more sunlight, so you produce more power. And then in winter, you produce less. So once we've got this, the power production model, we can then adjust the size of the solar PV array and the inverter to meet the needs of what the heat pump requires to produce that hot water. And then when we put those two curves together, we then come up with energy balance. So what we find is the most capital efficient way to combine these systems is to have an energy balance where annually over the year, the total amount of solar energy which we are producing is the same amount as the total amount of electricity which the heat pump is consuming. So when we put those two things together, we want to be around zero. Now, if we achieve that, that means that the operating carbon footprint of the system is very close to zero, because the energy required to drive the heat pump has been provided by the system. Now, there's going to be some overshoot in the summer and some undershoot in the winter, where you're producing more power in the summer than you're consuming, but less power in the winter than you're consuming. So there is the system does take power from the grid during the winter months and return power back to the building during the summer months. But the important thing is annually, the size of the system is in balance when you look across the extent of the year. The reason why you don't drive further with a bigger solar system than required is as soon as you start, let's say, oversizing the solar system, then the less capital efficient the system becomes. Ideally, what you want to do is the high temperature heat pump and the solar PV system, they're a very, very good fit together. It's like peanut butter and jelly. They just go together very well. And the reason for that is if every kilowatt of electricity which gets harvested from your solar system, you turn into 3 kilowatts worth of hot water, that in terms of capital efficiency, that is much, much better than using that 1 kilowatt of electricity to run an electric element or to run some lights or to run your computer or whatever your other power needs are. By far, preferentially, you should be using that kilowatt of electricity and turning it into 3 kilowatts worth of hot water. So when you arrange your system this way, the capital efficiency of the system is at optimal. And so when you then look at comparing costs relative to other methods of producing hot water, then the system really becomes a no-brainer. It's when you look at the numbers, it now intuitively makes sense. So rather than having to specify a system like this because of your green credentials or because you want to do the good thing for the planet or whatever, in terms of capital cost and return on investment and payback time, it is a no-brainer. You don't have to have a green imperative to use this technology. So as an example, once we've got the model built, then we can then drive out of the model some high-level QS, so we can cost the system. The engineering tool then gives us the running cost of the system, the running cost of alternative systems. So if you can QS what an alternative system is and the net zero system and then compare running costs, it's very easy to do return on investment calculations. What we find from most of the models that we do is if there's a lot of capital efficiency gained in centralizing your hot water. So if you were looking at doing a decentralized electric hot water cylinder model, and let's say it's 50 apartments, for us, we're at cost parity at 50 apartments, give or take. There's a little bit of wiggle room depending on the total shape of the system, but it's around that sort of numbers. So let's say, for instance, you've got a building with 50 apartments and you've got a choice. I can do 50 electric hot water cylinders, or I can do a centralized hot water system using this solar PV heat pump distributed network type of solution. We're at cost parity at about 50 apartments. So the cost of 50 electric hot water cylinders is about the same as the cost of the solar system, the heat pump, the tank, the blending valve, and the water meters combined. So it's a very, very attractive scenario. Then when you start looking at what the operating costs of the system are, then down at about 20 apartments, it's a 2 to 3 year payback time. At 50 apartments, you're at parity on the day you turn it on. At 100 apartments, it's actually cheaper than doing electric hot water cylinders. So just depending on what sort of solutions you're comparing to, this type of concept in hot water production is this technology has really come to maturity, and now it's really it will become the path of least resistance when it comes to installing these systems, just because the numbers really stack up so well. Okay, so in terms of process, I've kind of covered this a little bit already, but where we sit in the market is we're a design and supply company, and we interface with the engineering community. So if there's a hot water system to be done for a multi-unit apartment, typically there will always be an engineering company which is employed to design the system, and we work hand in hand with them. So what tends to happen is the engineering company will come with a performance specification. They will decide exactly how much hot water is required. We can give estimates of what we think we would do if it was up to us. They normally peer review that. We then produce a specification of all of the components which we would use to deliver that hot water, and then they will peer review that. If that design is adjusted or whatever, and once it's finalized, typically that goes out. We can produce at that point a high-level QS. So if you're working for a client and they're trying to make the decision about, okay, if I was going to go centralized gas or centralized heat pump, or I was going to use distributed electric hot water cylinders, we can compare capital costs of each one of those systems, and we can compare running cost of each one of those systems and carbon footprint. So then the client can really make a high level determination with like an informed decision about which way they want to go in concept. And then once that has been decided, if it turns out to be that yes, they want to go with a centralized heat pump style of system, typically then it goes out to tender. someone will win that contract, and then we have this wraparound service where we have installation support and we have commissioning support. And that's on site. So for each one of these systems, we actually send an engineer from our company out to the site to help the installer to oversee the installation of the system, and we're there during commissioning. So what we're trying to do is create this sort of wraparound service where we have the quantity surveying and specification at the front end, and then at the back end we have this installation support and we have commissioning support to try and make the process of using this sort of technology as smooth as possible. It is a relatively new technology, and so there is not a lot of experience in the market in using these types of technologies. So that's why we have this sort of wraparound support to help it be as trouble-free as possible. Okay, so here's a design of how the system actually looks. This might be a little bit technical for this audience, but it gives you kind of an idea of the shape. So I've spoken about redundancy. So this particular system on the left-hand side, there's 2 heat pumps. They're tied together with a small buffer tank. And then on the right-hand side, we have the hot water cylinders. So this particular system is 32 kilowatts of recovery with 2,000 litres of hot water. And so you can see how these systems are related. The heat pumps themselves are what we call indirect, so it's mechanical water. So the water that's inside the heat pump and inside the buffer and on one side of the heat exchanger is mechanical water. It stays in there forever and doesn't come out through your taps and showers. And then the water that's contained inside the hot water cylinders is potable water, so water that comes out for your taps and showers. So the two systems are kept separate using this plate heat exchanger technology. This is very common for centralized hot water production. You could substitute the heat pumps in the system to gas boilers and it would work in exactly the same way. So this sort of technology is used a lot. The control system which we use has got some quite neat features in it, which helps the capital efficiency of the system. So the controller, it does 2 functions. It has appliance control, so it'll cascade the heat pumps. So if there's only a small hot water demand just to recover some from one person having a shower or some losses out of the ring main or whatever the case may be, it can bring on just one appliance at 30% of its output and it can recover the system without spooling up all of the appliances. As the load comes on, the cascade controller sees that more power is required and then it modulates each appliance up as it needs to and then modulates them back down again as the load comes off. Automatically, once a week, it reorders the array, so whichever heat pump's done the most work now becomes the last priority heat pump, and the one that's done the least work becomes the first, and they'll just stack up in between. So the controller will control the appliances to maximize the life of them, to give them even work. The second functionality of the controller is it has modulating set point. So this might sound a little bit complicated, but in practice, it's very simple. So what we can do with the system to try and maximize the integration between the solar PV power and the heat pump operation. So again, just to cover off, if we're producing solar energy, our number one priority is to run that through the heat pump. So rather than just consuming it as 1 kilowatt of electricity, we can turn it into 3 kilowatts of hot water, which really drives that capital efficiency for us. So what we can do in the controller is we can set a minimum acceptable set point in the hot water cylinder of 55 degrees. So if the system ever drops below 55, doesn't matter whether it's day or night, the system will turn on, the heat pumps will spool up, and we will keep that hot water system at 55 degrees so we can provide enough hot water to the building. What we can do is we can logically connect the solar PV system to the heat pump. So they're not directly connected, they're not wired together, but what we can do is once the solar PV system goes above a certain threshold, so let's say it's above 30% production, we can then send a signal to the controller to do a dynamic boost. And what the dynamic boost does is it changes the requested temperature in the heat pump from 55 degrees up to 70 degrees. And so that then starts the heat pumps up. We've got solar, which is hitting our PV array, being turned into electricity, which is then being turned into hot water. And we store that extra energy in the hot water cylinders. So what that allows us to do is to have a solar PV system without having any lithium-ion batteries attached to it. And so that's a plus on two sides. One, lithium-ion batteries are quite expensive, and two, they're not very environmentally friendly. So by far, our best preference is to actually store that energy as hot water rather than electricity. And so that's what this functionality does. Once we're in solar production, creating electricity, the system will sense that and then dynamically turn the heat pumps on and start building energy, storing it as hot water in our hot water cylinders. Okay, so a third function which the system does is it's got Legionnaire's protection. And so what that means is if for some reason the cylinders have not been dynamically boosted up to 70 degrees within the last 24 hours, it will then send a request to the heat pumps to sterilize the tanks. So it'll do that. Typically what we'll find is you'll get at least some dynamic boosting every day. But if you don't, because the weather is terrible or because the solar system's not in production for whatever reason, then the system will sterilize the tanks automatically. It'll bring the tanks up to 60 degrees to make sure that they're safe for consumption in the building. So we've got these three possible set points which the system controller uses. 55 degrees, which is our minimum acceptable, 70 degrees, which is our dynamic boost when we're in solar production, and then 60 degrees, which is our sterilization temperature. And that all happens dynamically in the background. You don't have to you program it when you set it up, but under normal use, it'll just works itself. Okay, so one of the key components, obviously, we've got is the high temperature air to water heat pump. Again, the reason why this technology is starting to diffuse through the market now for hot water production is because of these new refrigerants. So R290, just to cover off, has a GWP of 3 and it's high temperature. So it allows us to produce 75 degree water. So previously with R410A or R32, which are kind of the R32 is kind of the industry standard gas at the moment. When you look through a lot of air conditioning appliances, they top out at about 60 degrees, so about a 62 maximum. And it's not quite hot enough to sterilize our tanks reliably. And so if you're going to use that type of system, almost always it'll have some sort of electric backup. And when you use electric boost, you're now no longer have access to that COP of producing 1 kilowatt in with 3 kilowatts out. It's 1-to-1. So the overall efficiency, the overall COP of the system is much less than what it is if you could just use the heat pump. So this is why now that this technology is really starting to be used more and more for hot water production is the R290 gas is really much better suited to hot water production duties than what the older gases were. One of the other technical features of R290 gas is what we call multi-pass. So it's very comfortable in rising the temperature a small amount. And this is a little bit technical, but one of the other gases which get used is called CO2. One of the problems with CO2, or one of the challenges with CO2, is what they call a single pass appliance. So to get a good COP out of a single pass appliance, it wants to have a very, very big temperature difference in the water which it operates on. So it's very comfortable having cold water coming from the street at 20 degrees, heating it all the way up to 65 degrees, and then putting it back in the cylinder, which is great on the face of it. But the challenge that creates is what do you do once your hot water cylinder is already hot? So if you've supplied a small hot water demand and your cylinder's gone from 65 degrees down to 60 degrees, now you have 60 degree water returning to the appliance. COP is nowhere near as good. And so you have to have some sort of other strategies to overcome that. The advantage with R290, relatively new gas, is it's multi-pass. So it's very, very comfortable having hot to warm water returning to it, only rising at 5 degrees and putting it back into the tank. So it's a little bit counterintuitive. If you're not coming from this world, you would think that, oh, if I can take cold water and immediately produce hot water, isn't that a big advantage? But in practice, actually, no, that's a limitation which you have to have a very particular hydraulic design to make that work properly. So gas appliances, they're all multi-pass. So this technology really is like a direct replacement for a traditional boiler system, which gets used a lot. So again, the brains of the operation is the controller. This controller has two basic functionalities. Just to cover that off again, it has cascade control, so it will control the multiple appliances, and it has this moving set point technology, so we can have our three set points which we use in the system: the 55-degree minimum acceptable, the 70 degrees for the dynamic boost, and the 60 degrees for the Legionnaire's protection. Okay, so I mentioned earlier that these systems are indirect systems. So in the heat pump, we have mechanical water, and then in the hot water cylinder, we have potable water, which is the water for the taps and showers. So we keep that water separate using this plate heat exchanger technology. And we have a range of hot water cylinders, commercial hot water cylinders. So we've got two basic sizes, 500 litre and 1,000 litre, and we like to run them in an array. So we'd never specify a system with just one appliance or just one hot water cylinder. If I needed 1,000 litres of hot water, I'd use two 500s. So we've always got some sort of redundancy built into the system. So if you have a problem with the hot water cylinder, you can isolate it, but you still run with at least half the capacity, depending on how big your array is. The other thing which is changed over the last few years is we now no longer do tanks bigger than 1,000 litre. What we tend to find is used to be common to do 2,000 litre tanks, but the issue you have with these bigger cylinders is when they come time for replacement, you can't get them out of the plant room because of the dimension of them. They're too wide, they're too tall. You just can't get them through standard doorways, and that creates a lot of cost when it comes to replacement. So typically now we're only using 500 and 1,000 litre tanks. The 1,000 litre tank will go through a metre wide doorway. It's 900 diameter. The 500 litre tank goes through a 800 wide doorway. It's 715 diameter, and they're both 2.2 metres tall for the 1,000 litre, so it fits inside a standard plant room 2.4 stud, and the 500 litres 1.8 metres tall. So in terms of actually siting the tanks, this is the sort of new philosophy which we seem to be following. Okay, so with a centralized system, we have to circulate through the water through the building at a constant temperature, and mostly this is for anti-scald. So while we need to sterilize the tank, while we need to keep the tank, we have to be able to get the tank above 60 degrees, and at some point we'll be doing dynamic boosting, getting the tank up to 70 degrees. We don't want to distribute 70-degree water through the building, and so we use this electronic tempering valve to set the water temperature which enters the building at 55 degrees. So this is mostly for anti-scald purposes, also for heat loss out of the ring main. The lower you keep that temperature, the less heat loss you have. If you're in particular environments like a rest home environment, this is normally set at 45 degrees, again, just because for anti-scald, older clients have more sensitive skin, and so we use a lower water temperature in that application. The advantage with this electronic style mixing is it has data logging built in. So every hour it records what temperature enters the loop and what temperature returns from the loop. It's also Modbus compatible, so you can connect it to the building management system for off-site maintenance. So what we find is these valves are very good for troubleshooting. So if there's a complaint or a problem in the building where they say, oh, I don't have hot water at a particular time, you can go back to the controller and see whether that's being happened at production in the plant room, or if the water leaving the plant room is at the right temperature, then you know you've got a problem actually inside your building. So yeah, it's a very good technology, and this is being used more and more around in this application rather than using thermostatic mixing valves like we used to. It's going electronic now. Okay, in terms of charging, so when you produce your water centrally, then in a lot of applications, they'll also want to charge the client. So in multi-unit residential, if you've got distributed hot water production with hot water cylinders in the room, typically you just have a cold water meter, and then the energy for the hot water meter comes from the electrical board which feeds the cylinder. In this application where we're producing water centralized, we have now two water meters in the apartment, one for hot, one for cold, and you can have them either wired or wireless. The wireless system comes to a central GPRS hub, and then that sends an email out every month, and you can then use that for back charging. We also have a Modbus wired system, which will connect into a building management system if they're using that there. So there's a few options for this. And so this really completes the system where we have the production, the distribution, and the metering all in one integrated package. Okay, so I'll just run through a quick worked example, which will just help give you some sort of framework about how these specifications actually look. So in this particular example, it was 57 apartments and we had 119 people in total. It was in Auckland, and we were providing 40 litres per person. So it was mid to high end residential. So the production requirement to shower these 119 people was 4,700 litres, and the system which we specified was 2,000 litres of storage with 64 kilowatts of recovery, which gives us our 4,700 litres of water. Now, what the engineering tool does, as you manipulate your storage and your recovery, it gives you the performance of the system. So we can see here the recovery period. So after serving that first peak period of water from 6 a.m. to 8 a.m., it's taking 3.9 hours to then recover the system ready for the next peak period. Now, the next peak period isn't going to happen typically until 6 p.m. So we've got a big window in the middle of the day. And what we want to do is we want to arrange the system so that when the sun is shining, we are running that solar PV system and preferentially sending it to the heat pumps. So when we design centralized system with gas appliances, typically we would have smaller storage and higher recovery. And the reason for that is gas appliances on a cost per kilowatt basis are very cheap. So they're a very big hammer. So you get a lot of kilowatts for not very many dollars. Air to water heat pumps are quite expensive on a cost per kilowatt basis. So it makes sense to have proportionally higher storage with proportionally slower recovery. And that also works in with our solar window. So the peak solar window during the day typically is from 10 a.m. to 2 p.m., about 4 hours. So if we can engineer and design our system so that our recovery period coincides with our peak solar production, then we'll get maximum capital efficiency when it comes to size of our solar array, size of our heat pump, size of our storage. And so when we're specifying the system, this is what we're looking at. What is our recovery period? And ideally, we want to get it around about 4 hours. Because what you don't want, if you put in more heat pumps, that does two things. More heat pumps means that obviously more capital expensive. It means that you've got to have a bigger inverter because you're driving now more heat pumps. And if you recover that hot water system in 1 hour, now you've got 3 hours of your solar window, which you're not converting that energy into 3 kilowatts worth of hot water. You're consuming it as 1 kilowatt of electricity. So the capital efficiency of the system goes down quite a bit. So that's what this tool allows us to do, is get a window into, okay, how's the system actually going to operate? Am I kind of lining up the size of my solar window relative to my production and these things? So that's the first thing we look at is recovery period. And so for this particular system with 64 kilowatts of recovery, it's recovering in 4 hours, which is good. It also gives us a shape of how the dynamic overboost looks. So if I've got 2,000 litres of water and I'm taking that water from the 55-degree minimum acceptable and I'm boosting it up to 70 degrees, that takes 35 kilowatt hours of energy to do that. But that is only costing me 11.2 kilowatt hours of electricity. And that's because of the COP of the appliance. So that's the power of the way the system works. I supplied 11 kilowatts worth of electricity. It gives me back 35 kilowatts worth of hot water. And it tells me that that dynamic overboost takes about half an hour. So now I've got the general shape for the system from recovering from that first peak period up to my peak temperature of 70 degrees is taking about 4.5 hours, which is a pretty good fit. So we're kind of happy with that specification. So once we've got those pieces of the puzzle lined up, where we know how much storage we've got, what size appliances, heat pump array I need, now I can use that to drive the size of my solar system. So in this particular system, I need a 20 kilowatt inverter and I need 61 solar panels. And so this creates my offset. So those 61 solar panels take up about 102 square meters of roof area. So now at a very high level, I can see whether this system fits practically within the building. I know that I've got 4 appliances, they take up this much space. I've got 2 hot water cylinders, they take up this much space. And I've got 61 solar panels and they take up this much space. So without doing a lot of engineering work, without incurring any cost, we can see the practicality of the system relative to the building that we're working in. So it gives the client a very low cost way of exploring this as an option without having to invest in any sort of real money in producing it. Okay, so the other thing which the tool will provide us is it gives us various running costs. So as an example, if I was going to produce this 4,700 litres of water using a traditional electric element distributed hot water production model, the running cost on that is $27,000 per year. If I was going to do the same system but with natural gas, then the running cost is $7,400, and with the heat pump without offset is $8,700, and then with offset is practically zero. So the total amount of energy which I'm producing in the year is the same as the total amount of energy which I'm consuming. So you can then very quickly do some sort of capital payback, some return on investments of a cylinder system versus the capital cost of a cylinder system. I know the running cost of a cylinder system is now $27,000 a year, and then I can compare it to a net zero system with offset, without offset, a gas system. So all of these sort of options now you can quantify and make informed decision for the client about, okay, what really makes sense for this application. And then we do the same thing, but with carbon footprint. So the carbon footprint which we have for an element system is 11,500 kilos of carbon. With natural gas is 23,000. With heat pump is 3,700, and then with offset it's practically zero. So for a lot of clients, when we're looking in the institutional and government sector, their key metric for making decisions is what's the carbon footprint. And so you can start with a number of different designs of systems with different capital costs, and then you can compare what the carbon footprints are. So then the client can make an informed decision about, okay, I need to spend this much money to reduce my carbon footprint by this much. And so then again, they can make this informed decision without investing a huge amount of money in engineering time. So we can produce these models very quickly and without any cost. So that really gives to the market the ability to make these informed decisions, which is very powerful. Okay, just want to jump back a couple on the slides. Let's go back one more. Okay, so with the output, what we have is basically an equipment schedule. Tells you how many appliances there is, how many cylinders. So we can use this for a number of things. One, we can derive a high-level QS where we can give a realistically expectation of what the installed system would cost, and we can also scope it for space because we know exactly how many appliances there are, what size the appliances are, how big the tanks are, all that sort of thing. So very quickly you can sense check the system both in terms of practicality and in terms of cost. The model then also drives those metrics which we just looked at in the text. So it gives you a graph for the power production model, gives you a graph for the power production model, and then the energy balance. So this is the basic shape of the system performance, and it drives through some of the key metrics like how many solar panels, how much roof area, all that sort of stuff. Then we just have some graphs for the running cost comparisons and the CO2 comparisons, which is that same information just in graphical form. Basic schematic of how the system looks. So this particular system with 64 kilowatts of recovery, we've got 4 appliances in cascade and then 2 1,000 litre hot water cylinders. So again, this just allows you to then really get your head around what the space requirements are, the basic shape of the system, how it kind of fits together. And then we do a specification sheet on each one of the primary components. So these have got the dimensions on, it has the power in, the performance out, all sorts of interesting things. And we select one of those for every one of the components. So this is the high-level QS, which normally then goes out as part of the tender specification documents. The controller, which we've talked about, so that this modulates the cascade, also does the moving set point. the cylinders, the heat exchanger modules, the electronic mixing valve to distribute the water through the building. We have a UVR on the return to sterilize the loop, and then the water metering system. And we can do the water metering system either wireless or wired. We have a partnership with a solar PV provider. We don't do solar PV ourselves, but we drive the specification for it. The partner which we use Fronius inverters and REC panels, but if the client has an existing relationship with a solar provider, that's no problem. We just drive the specification and say, okay, if you want to create this offset, this is the shape of the solar system you need, this size inverter, this many panels. That goes out to tender as a separate contract. Combining these two systems together is very simple. It's a logical integration, just where there's a contact that closes in the inverter, my system sees that and then does the dynamic boosting. So it's pretty much compatible with all of the major inverters on the market. Okay, so that's an example of what the pack would look like when it comes to the net zero. So I'll just give it the front cover. Okay, so we're open for questions. It is a big download. Hopefully, you've been able to understand sort of the basic gist of what we're doing. Very happy to answer any questions which you have.
Awesome. Thanks, Darren. That was yeah, like you said, a big download, a lot there, but I think it was pretty straightforward. I kind of mostly understood it, but I do have some clarifying questions because I've been writing them down as I've been watching here. So you mentioned, and I'm going to already challenge you here, if that's okay with you. You mentioned centralized for about 20 apartments. If you go above 20 apartments, it becomes more economical to go with a centralized system. And for me, that's very typical in Canada. But for some reason here in New Zealand, people always argue with me saying, nah, it's too complicated. There's fire valves and different metering and blah, 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 blah. Are people they just don't like it because, well, like, what's the holdback? Why am I always being argued against with the centralized systems, out of curiosity?
Centralized systems in New Zealand are pretty common. There is a lot of centralized systems which get used in the rest home environment and hotels and hospitals and quite a bit of apartment work in Auckland. I think most of it's fear of the unknown. And again, I think one of the fears is the redundancy factor, where if you have a problem with a centralized plant, it takes out your whole building. But in our experience, the capital efficiency you gain by going centralized there's really the reason not to use it is very small compared to the reason to use it. So that capital cost break even of 20 units, that would be if it was a gas system, because the gas appliances are very cost effective. For a heat pump driven system without PV offset, you're looking typically at about 40 apartments, and with PV offset is about 50 apartments.
Sure, just because of the upfront cost, I guess, eh?
Yes.
Is kind of fair. Cool. Makes sense to me. So I will I'll suggest this on projects moving forward. See what we can do here. How is the electricity tank for a building? In terms of, okay, so you mentioned these kind of little schematics and plans. What sort of room does this take up? Because that's another argument that I get when I'm in a design meeting. It's like, oh, where are we going to put this equipment room? Where are we going to put this plant room? The answer is usually on the roof. Does that make sense for these types of systems? Having the tank, heat pump, etc., right next to the solar array, and then you have pipes going through the building? Or what's the kind of, like, if you have, let's say, a 4-story building, I don't know how many units across, but you get to that 50 units. What does the distribution look like? Where do you put this? How does this look on a building?
Yeah, typically the ideal location with the path of least resistance is the roof. That can't always happen. Sometimes the buildings are at height limit. So in terms of the system's split into two, where you have your outdoor units and then you have your plant room, which sits inside. And if you're just doing a plant room for the hot water production, Like how big was that job which we looked at? 59 apartments, I think it was, 57 apartments. That's two 1,000 litre cylinders. So realistically, you can fit that in a plant room, maybe 2.5 by 3.5. So it's not a massive footprint for the plant room. And then you've got 4 appliances. And so those appliances can be stacked on top of each other. So the footprint of the appliances isn't huge. And you can also split them apart. So you don't have to have the cylinders and heat pumps on the roof, for instance. You might just have the heat pumps on the roof and then the cylinders in the basement. So you can pipe in between.
Interesting, because that's what I was going to ask. Like with these tanks, I'm assuming you need some structure for them. But if you can put them in the basement, then that kind of alleviates that, which is kind of interesting. Okay. It's seeming like it makes sense.
A full tank's about 1,100 kilos, so it's not it's heavy, but it's not an elephant.
And am I crazy for feeling like that's not enough for 59 apartments? Like, are we talking everyone's showering at the same time, full blast hot water, and 1,000 liters of a tank is enough because the heat pumps are, I guess, filling the tank as you're going? Is that how it's working here?
Yeah, so we've got an array of cylinders. So in that particular job, we had 2 1,000 litre tanks. So we've got 2,000 litres of storage. And that's one of the things of it's why you get such high capital efficiency when you centralize the plant, where if you're thinking, okay, I've got 50 electric hot water cylinders, they're all, well, let's say for easy numbers, 200 litres each. Well, that's 10,000 litres of hot water we're storing. But you're recovering at a rate of 3 kilowatts each. So because typically you have a peak period of 2 hours where you shower everybody in the building. Not everybody gets up at 7 a.m. on the dot and all jumps in the shower at the same time. So you can use that use pattern to your advantage, where you have where you even out the hot water production over this 2-hour period. So you get 2,000 litres of hot water stored, ready to go at the start, and then you can recover it at a rate for this particular system of 64 kilowatts. So compare that to a single 3 kilowatt element. You have this kind of, not quite, but semi-instantaneous hot water production, where you've got the storage capacity you start with, and then you can recover it on the fly as you use it over those next 2 hours.
Interesting. Okay. Then you mentioned, because I was thinking when you were showing those kind of graphs, you were showing those and I'm like, would a battery help? But then you kind of said, well, it's better to keep water as your battery because you're not using lithium ion to do that, which makes a lot of sense to me. But when you have all of that kind of stuff going on during the day, I guess that would only work in the winter. But what I was wondering is, can you use the same hot water for heating in your house, radiators, underfloor heating, stuff like that? Or is it a different temperature, has to be a different loop? How does that work?
Yeah, so this is very focused on domestic hot water production. When you start using that energy for other applications like space heating, then the advantage of having this out of phase, where you've got the hot water stored for the morning peak and then you recover it during the day when the sun is shining, that drives a lot of capital efficiency. And so when you start to multi-use this plant, that kind of falls apart.
I see. Fair. Okay, so
and
you want to
just one other point, just while I remember, where you were saying, oh, why don't we use a lithium-ion battery? Just remember, if you're using a lithium-ion battery, that 1 kilowatt of electricity you're storing is 1 kilowatt of electricity. Where if we're storing it as hot water, that 1 kilowatt of electricity I'm storing is 3 kilowatts worth of energy, because it's running the COP through my appliance.
Sure. And there's not really
as a specific example, on that last system that we did, we were storing 35 kilowatt hours worth of energy in our overboost, going from 50 to 70. Now, if you're going to do that in power walls, that's 3 power walls at 15k each. There's 45 grand worth of power walls, which we're storing as hot water. So it's very, very capital efficient to store energy as hot water relative to lithium ion.
Sure. And there's no real need to have to heat water when the sun's not out, because you've already sized the system such that there's enough kind of in there that it just kind of works, I guess. Okay.
Ideally, you want to be coasting.
Sure. It's a different way to kind of make this happen. It's a kind of a weird thing to wrap your head around, but it makes sense. Okay, so we got that. Okay, so another kind of out there thing. when you're creating hot water with the air to water heat pump, you're also creating cold air. Is there any way to use that cooled air during the summer for air conditioning of a house, do you think? Out of curiosity. I'm just trying to like put things together here. It's a little bit more complicated than it needs to be, eh?
Yeah, typically no, especially not on this scale. Like it is a different different situation if you scale it down to the house level, where on the commercial side, the being able to actually capture that cold air and then route it through the building becomes very costly and impractical.
You might as well just use a heat pump at that point. Yeah, fair. Okay, cool. Yeah, okay, cool. I think that's about it. I was wondering also, like you said, there's usually a ring main or kind of a a loop back to the system when you're using a centralized system. Where does that usually go? Is it just in the same core, in the same kind of riser, or is it actually kind of going out somewhere else, just the same riser? Okay, I was going to say, can we use it
Same
for heat?
riser?
Cool.
Yep. Yeah,
Cool.
yeah. You go out and back next to each other normally.
Sure. That makes sense. Okay, cool. Yeah, I think that the main thing that I was thinking here is that you're kind of seeing the sustainability thing from the operational standpoint, and I think that's a very important thing because I think we're not there yet here in New Zealand. We're not there yet anywhere in the world, really. Not like as a common thing. So it's really cool to see kind of an interesting system that really kind of wraps everything together and makes everything work as one.
Yeah,
that's all the questions I had.
When we're talking about
sorry.
embodied carbon, there's a really long way to go with these technologies. Like they come from all over the world. They're not easily recyclable. Like when you look at it through that lens, they're terrible. But then when you look at it through the lens of its operating life, it's like you can produce all your hot water for 15 years with zero carbon footprint. Well,
sure,
that's pretty powerful.
Pretty good. Yeah. It's got, but that's the thing. We're attacking this from all angles, and that's what we kind of have to do. You can't let the perfect be the enemy of the good. So, I got one question in from online. Actually, I didn't notice before. Someone's looking to put a system into a 2-story, 3-bedroom home with a 3-degree pitched roof and heating pipes in concrete floors to ground and first floor. What system would you recommend? This is a very specific question. Maybe. I think your email will be on the event page here. Maybe they just email you directly on that one.
Yep.
Or do
we do this type of technology as well. We do a lot of space heating with underfloor heating. We also do radiant cooling systems, all driven from air to water heat pump, and you can create offset with solar PV. This particular system is very focused on high capacity hot water production for multi-unit residential.
Sure. Yeah. Got to be its own thing to work efficiently. Cool. Well, I think that's all we have. We're already 4 minutes over, so I think I'm going to wrap up. But any last thoughts before we let you go for the day?
No, I don't think so. That was, it's a lot of information to really get your head around. I guess one of the key takeaways is if you've got a building which is kind of in this shape, more than 20 or 30 apartments, and you're thinking, and you've got a client who's interested in reducing carbon or even containing running costs, which is practically everybody, then send us a brief and we can produce this type of feedback quickly and with zero cost. So then the client can make informed decisions.
Awesome. Thank you so much. Yeah, get in touch. Cool. Well, have a good rest of the day and nice speaking to you. See you soon.
Thank you very much. Bye-bye.